No, it's still sharing.
Yeah. Okay, so when we train neural premise selection models, the data set is definitely the most important part. So actually we managed to extract premises from proof steps from the entire AFP in Isabel, which is pretty nice, thanks to Albert and other collaborators. So we extracted about 700,000 proof state and premise pairs for training of our models and more than 100K unique premises, which is pretty nice. So actually, first we just inspect the retrieval metrics of our embedding-based premise selection models by just looking at how many premises we need to retrieve in order for the retrieve part to contain the ground truth. So basically, they recall at K metric. So what you can see from here is that if we basically increase the capability of the model, so the first model is basically a one-layer transformer, which is basically just a bag of words, very simple model. Then if we just make it like multi-layer transformer, it's already way better. And also, if we just increase the batch size in the batch contrastive learning setup, it also gets much better, which is, it shows that we just need to, maybe we just need to scale these models up, which is some sort of hypothesis. So the first thing we actually test is very simple. So we just take this embedding-based premise selection model, and we want to retrieve top K premises for some top-level proof state. And then we just do metrics, and that's it. So the question is, how good is this? So it works surprisingly well. So you already see that even using a single model, you get proof rates that are significantly less than Sledgehammer, but they're getting pretty close, which is surprising. And even if we combine two different checkpoints of the same model, you already get improvement, which shows that we can actually, maybe we can just take a couple of checkpoints and you can be equal to the Sledgehammer, which is...
Sorry, can you explain what's that checkpoint?
So basically, I'm talking about different parameters of the model. So you train a model once, get some parameters, you evaluate, then you take like the parameters from a different training step, let's say like a couple of thousand training steps earlier, and then you just evaluate the model as well, and then you sum the results. So you just evaluate both of the models, and you just use both of the models during the evaluation. That's the sum of the solutions.
You use both models only for the premise selection, or you run metrics twice?
Actually, I need to run metrics twice because just the list of the premises is different for both of these models. So if I take top K, I need to, yeah. So that's a good point. I mean, we need to improve the efficiency, certainly. Oh, yeah, go on. Yeah.
Yeah, I'm just curious, do you know if for Sledgehammer versus the Netics with the translation model, is there overlap?
Oh,
like,
that's a very good question. I mean, that's the next slide basically. So let me just go. So the one more interesting point is that actually there is a surprisingly small intersection between our premise selection model with Metis and the Sledgehammer. So it seems that even though we somehow mimic the Sledgehammer because we just do Metis, it's just what the Sledgehammer outputs, we still get a different set of problems solved. So if we just sum the Sledgehammer problems solved by Sledgehammer and our method, we actually get pretty significant improvements. But it's also can motivate us to improve, to understand, like to improve our method, because we are still missing something to match the Sledgehammer, because we still don't manage to solve half of the problems done by Sledgehammer. We just solved some new problems, but that's very interesting.
Can I ask, how are you running Sledgehammer? Is it the version with slicing on multiple CPUs, or is it just the first slice?
I guess it's just the default without any parameters. Like, on just running sledge.
So in what mode? Is it the Mikuła setup or is it on the individual roles?
Maybe Albert can answer this.
How are you running Sledgehammer?
Like 30 seconds of timeout.
But how? So by default, it checks the number of CPUs available, and depending on this, it scales itself. Right. So that like you have to say something about what hardware did you give it in order for me to know what it actually runs inside. So depending on the number of CPUs, it also will run certain provers or not.
I see. There are like 96 cores on our machines.
And it assumes it can get all the 96 cores for one Sledgehammer call.
Yeah, that's if the default is able to utilize that, then sure. Okay, so here is the question: can we already implement that? Because the problem is that in Isabel we already have Sledgehammer, which is nice, but there are some other provers that just don't support hammers. And maybe instead of re-implementing this, we can just use this kind of simple neural setup. So one thing is that we actually need a lot of data to do that. So that's the condition. But in Lean, there is actually quite a lot of data, I believe. So maybe that's the way to go. So it's actually very hard to, I think there have been some efforts on actually implementing hammers in Lean, but I don't know about any successful effort. So it's very hard to implement them. And also yesterday, there was this complaint about this thing that you actually need to wait 10 seconds for the Sledgehammer. That's more of a joke, but who knows, if we optimize these models, we might get some better runtime. And also, we don't need a GPU, basically, because these models the premise section models are just not very demanding in terms of hardware. They're very small, so like 15 million of parameters. You can just run them on the CPU. So basically, no GPU is needed for inference. So you could ask, like, because we are using TPUs, so we already don't need GPUs to run them. but actually, it seems that they are pretty easy to run on the CPU, which might be another advantage. Because if you require a GPU to run this, it might be already limited in the academia, especially. So let me explain the part about language models, because now we talked about the premise section. So the standard language model that generates proof steps or tactics, the only input of the model is some sort of a proof step. So it doesn't have any access to premises. That's a very simple model. We just generate some sort of a proof step. But our model, we actually, when we do the retrieval for the current proof state, we just prompt the language model with top K premises retrieved by the premise section model. So the entire input of this model is a list of premises which the premise section model thinks are most relevant, and also the proofs. And we also generate the proofs, which possibly utilizes those provided premises. So what are the actual, so what's the deal? So we actually run some experiments when we prompt the model, we compare the standard language model, which is a state-only model baseline here, with our model where we prompt the premises, and we already see some improvements, like 3% of the proof rate. And what's more, we see that this model can solve problems that originally in the AFP, their proofs utilize some premises. So it's more capable of solving problems that require at least one premise in the original proof. So we actually wanted to inspect if these models gain some new capabilities. So if they actually use the premises provided as the context. So actually we have some theorem, and it seems that our model with the our premise guided language model has generated some proof which uses the premise. And actually it seems that we have checked that this premise is from our test set. So it's not defined in a training set, which means that standard language model just cannot access this premise, which means that we have actually retrieved. So we have already seen a number of examples where we are capable of retrieving those premises from out of the training set, which means that the model actually somewhat generalizes. So we have our new premises, we can basically define some new premise and we can prompt the model with it and maybe it will use it. So basically, this is still a work in progress. So we definitely expect stronger models and bigger improvements from this technique. So yeah, thank you for your attention. If you have some questions, please.
Are there any questions?
Can you keep this premises also sledgehammer?
Oh, but Sledgehammer already does premise selection, right?
Yeah, but you can do batch selection. So why not
Yeah.
repeat this?
Yeah, I see. Actually, we have explored this path, but turns out that it's not really trivial to add like this capability to Sledgehammer. Just using Metis is very simple, right? And we actually don't know how to do this with Sledgehammer. So
It is easier than that.
oh.
It is easier than that. It's one liner.
Oh, really? Yeah, we haven't tried that, but if it's very simple, then we can definitely try it. Yeah, that's a good point.
What is I didn't exactly get what is data what does the data set look like?
Okay, so basically we just take the AFP and we take some held out theorems from the AFP, and that's our test set. And the training set is just the entire AFP. So archive of formal proofs. Right?
Without those theorems.
What do you mean?
Without those theorems that you took out.
Yeah, without the held outs. Yes.
And do you split it randomly or chronologically?
Just random.
So that means that a premise, for example, is in your test set, but it could still be used in your training set.
Yeah, but we inspect that. I mean, if we look at the qualitative results, we check if the premise is in the trainings, and we haven't seen those premises in the trainings. So
when you see that you haven't seen them, they weren't defined or they weren't used.
I think they weren't used. Yeah. There is still a possibility that they might be somewhere in the proof state, actually. Yeah, that's a good question as well. I mean.
Okay, last question.
Have you deleted the persistent file of Sledgehammer?
Can you repeat?
Have you deleted the persistent file of Sledgehammer? Match state.
Oh, no. I'm just using the default setup in the Sledgehammer. Just one line.
Sledgehammer uses what you learned in the past. So maybe.
Oh.
I can click it.
Oh, I see. So you can run Sledgehammer multiple times, right? And it gets better. That's your point?
Yeah. So
Oh, I see.
it might not be their comparison. So I can.
I see. Yeah. That's okay. Yeah.
All right, thank you very much.
Thanks.